Deep within the moon's core, something unexpected is happening that has renowned physicist Michio Kaku issuing urgent warnings to the scientific community. Recent seismic signals detected by advanced monitoring systems suggest our celestial neighbor isn't the geologically dead world we once believed. These mysterious tremors from the lunar interior could reshape our understanding of planetary evolution and potentially impact future Artemis missions. As humanity prepares to return to the moon, these discoveries reveal that our closest cosmic companion still harbors secrets that could change everything we thought we knew about lunar geology. The moon's hidden geological life. What if everything we thought we knew about the moon being a dead, inactive rock was completely wrong? For decades, scientists have described the moon as essentially geologically inactive, slowly cooling as it orbits Earth. This view portrayed our celestial neighbor as a silent, frozen world in the final stages of solidification with nothing interesting happening beneath its surface. Recent discoveries are shattering this long-held assumption. Advanced seismic monitoring has detected unexpected signals emanating from deep within the moon's core, suggesting ongoing geological processes that challenge our fundamental understanding of lunar evolution. These aren't minor tremors but significant seismic events that indicate the moon's interior remains far more dynamic than previously imagined. The implications extend beyond mere scientific curiosity. As NASA's Artemis program prepares to establish permanent human presence on the lunar surface, understanding the moon's internal activity becomes crucial for mission safety and success. These seismic signals could indicate areas of instability that might affect future lunar bases, mining operations, and long-term human habitation plans. Michio Kaku has been particularly vocal about these findings, emphasizing that what we're witnessing could represent the final chapters of the moon's geological story, a rare cosmic window that humanity is fortunate to observe and study before it disappears forever. Michio Kaku's scientific warning. Renowned theoretical physicist Michio Kaku has emerged as one of the most prominent voices, warning about the significance of recent lunar seismic discoveries. During his recent lectures and public appearances, Kaku has emphasized that these signals from the moon's core represent far more than routine geological activity. They could indicate fundamental changes occurring within our celestial neighbor. Kaku's concerns stem from the timing and nature of these seismic events. The moon's core, which scientists believed was in its final stages of cooling and solidification, appears to be undergoing unexpected changes that could have long-term implications for the Earth-Moon system. These aren't gradual, predictable processes, but sudden, measurable events that suggest something significant is happening deep within the lunar interior. The physicist has stressed that humanity exists in a unique cosmic moment. We're witnessing the moon's geological death throes, processes that operate on timescales we can barely comprehend. In another billion years, the moon's core may freeze completely solid, making current observations irreplaceable scientific data about planetary evolution. Kaku's warnings extend beyond academic interest to practical concerns about future lunar exploration. Understanding the moon's internal dynamics becomes crucial as humans prepare to return to the lunar surface and establish permanent settlements. The seismic activity could affect everything from habitat placement to resource extraction operations. NASA's advanced seismic detection systems. NASA's cutting-edge seismic monitoring technology has revolutionized our ability to detect and analyze lunar geological activity. The agency's latest instruments represent a quantum leap beyond the Apollo-era seismometers that first detected moonquakes in the 1970s, offering unprecedented sensitivity and precision in monitoring the moon's internal processes. The Farside Seismic Suite, scheduled for deployment around 2026, will be the first seismometer placed on the moon's far side. This positioning is crucial because it allows scientists to triangulate seismic events with much greater accuracy than ever before. The instruments are approximately 30 times more sensitive than their Apollo predecessors, capable of detecting even the faintest tremors from deep within the lunar interior. Additionally, the Lunar Environment Monitoring Station near the South Pole will provide continuous seismic monitoring for extended periods, unlike the limited-duration Apollo missions. This long-term observation capability is essential for capturing rare events and establishing patterns in the moon's internal behavior that might otherwise go unnoticed. These advanced systems might finally confirm whether the moon experiences slow quakes tied to core readjustment, similar to Earth's slow earthquakes that take days to subtly shift stress. Such phenomena could explain the mysterious seismic pulses that have drawn scientific attention and concern from researchers like Michio Kaku. The moon's internal structure revealed. So, modern analysis has revealed that the moon's internal structure is actually far more complex than we previously understood. The lunar core resembles Earth's in miniature, featuring a solid inner core that's surrounded by a fluid outer core, but with some unique characteristics that make it especially interesting to planetary scientists. The moon's inner core, for instance, has a radius of about 240 kilometers, and is primarily composed of iron, surrounded by a partially molten outer core that extends to about 350 to 360 kilometers. This structure generated a significant magnetic field billions of years ago, much like Earth's current magnetic field, providing evidence of ancient geological activity that has since diminished, but hasn't entirely ceased. What makes recent discoveries particularly fascinating is that the core didn't just switch off after cooling. Instead, it appears to be experiencing these final phases of activity that modern instruments can now detect. The entire moon is actually shrinking slightly in volume as it continues to cool, causing its brittle crust to wrinkle and form ridges or scarps. Some of these surface features are remarkably young in geological terms, like as recent as 200 million years old, indicating that cooling and contraction processes are still happening today. The ongoing seismic activity confirms that the moon is still adjusting to these internal changes, making it a dynamic rather than a static celestial body. Artificial intelligence uncovers hidden lunar secrets. One of the most remarkable aspects of recent lunar discoveries, honestly, involves artificial intelligence analysis of decades-old Apollo seismic data. Scientists have been feeding Apollo-era seismic recordings into modern machine learning algorithms, and the results are just revolutionizing our understanding of lunar geology. These precious recordings from Apollo seismometers have been sitting in archives for over 50 years, but they're now revealing secrets that were hiding in plain sight all along. When Apollo astronauts first deployed seismometers on the lunar surface, computers were room-sized and had less processing power than today's smartphones. The analysis techniques available in the 1970s were, well, primitive compared to what we have now. Modern AI can detect patterns and anomalies that were simply impossible to identify with 1970s technology. These sophisticated machine learning systems can distinguish between genuine lunar activity and instrument artifacts with, honestly, unprecedented precision. Patterns that human analysts dismissed or never even noticed are now being flagged as significant geological events. NASA scientists describe this process as revolutionary, comparing it to having a conversation with someone for 50 years and suddenly realizing you've been missing half of what they've been saying. The AI analysis has identified thousands of previously unrecognized seismic events, suggesting that the moon's interior is far more active than anyone realized. The Earth-Moon gravitational dance. The relationship between Earth and Moon is, in fact, a gravitational partnership that has shaped life on our planet in some pretty profound ways. The Moon acts as a gravitational anchor, preventing Earth from wobbling chaotically on its axis, and maintaining the climate stability that allowed complex life to evolve and thrive. Michio Kaku often emphasizes that Earth is unusually stable for a planet its size. Most planets would wobble chaotically, but the Moon holds Earth steady, sort of like training wheels on a bicycle. This stability has enabled the slow, steady development of ecosystems and eventually human civilization. Earth's tilt of 23.5 degrees, which is responsible for our seasons, would change unpredictably without the Moon's stabilizing presence. The Moon's gravitational influence goes beyond just creating ocean tides. It also creates these slight bulges in Earth's crust. This tidal flexing generates heat through friction, contributing to our planet's internal warmth and geological activity. It's kind of like Earth receiving a constant, gentle massage from the Moon's gravity, helping maintain its dynamic interior. Any changes in the Moon's core structure could, in theory, subtly influence this delicate relationship over geological timescales. The seismic signals that concern scientists like Kaku might indicate mass redistribution within the Moon that could eventually affect Earth's climate cycles, though, such changes would happen over thousands of years, rather than within human lifetimes. Risks to future lunar missions. As humanity prepares to return to the moon through NASA's Artemis program, understanding lunar seismic activity becomes a critical safety concern rather than merely scientific curiosity. The recent seismic signals detected from the moon's core raise important questions about the stability of potential landing sites and the safety of future lunar habitats. NASA's analyses have identified thousands of young tectonic ridges on the lunar surface, some potentially still active today. These ridges indicate areas where the moon's crust is under stress, creating potential hazards for future missions. Unlike Earth, the moon's crust lacks water circulation to heal cracks naturally, meaning that once fractured, the brittle lunar surface remains vulnerable to further instability. Future Artemis missions or private mining operations might inadvertently drill into areas near fault lines without fully understanding the consequences. The lunar regolith, the layer of loose, fragmented material covering the moon's surface, sits atop a complex network of faults and stress zones. Mining operations that disturb this delicate balance could potentially trigger moonquakes or surface collapses. The stakes are particularly high because lunar bases will be completely dependent on their structural integrity. On Earth, earthquake-damaged buildings can be evacuated while repairs are made. On the moon, a habitat breach could be catastrophic, exposing astronauts to the vacuum of space with little warning or escape options. The moon as a planetary laboratory. While we often think of the moon simply as Earth's companion, astronomers and planetary scientists view it as a perfect laboratory for understanding the evolution of countless worlds throughout the galaxy. The moon represents an intermediate step in planetary development, larger than asteroids but smaller than Earth-like planets, providing crucial insights into how different-sized worlds evolve. Watching the moon transition from a molten core to a solid one offers glimpses into how exoplanets evolve, whether they can maintain protective magnetic fields, and their potential for supporting life. One of the most critical factors for habitability is a planet's magnetic field, which shields its surface from harmful cosmic radiation. These fields are generated by molten, electrically conductive cores. The moon once possessed such a protective field, but as its core cooled, that protection faded. By studying the moon's seismic signals and understanding exactly how its core is solidifying, scientists can develop models predicting how long smaller rocky exoplanets might maintain their protective magnetic shields. This knowledge proves vital for identifying potentially habitable worlds among the thousands of exoplanets discovered by space telescopes. The unexpected seismic pulses from the moon's core provide new data points for these models, helping scientists understand planetary evolution across the universe. Advanced monitoring technology. NASA's next-generation lunar seismic monitoring systems represent unprecedented technological advancement in our ability to study the moon's internal processes. These instruments far surpass the capabilities of Apollo-era equipment, offering sensitivity levels that can detect even the most subtle geological events. The Farside Seismic Suite will mark the first time humans have placed seismometers on the hemisphere of the moon that never faces Earth. This positioning allows scientists to triangulate seismic event sources with much greater precision than previously possible. The instruments are 30 times more sensitive than Apollo equipment, capable of detecting faint tremors from deep within the lunar interior. The Lunar Environment Monitoring Station will establish long-duration seismic monitoring near the South Pole, where Artemis missions plan to build permanent human presence. Unlike Apollo instruments that operated for limited periods, this system will continuously monitor lunar seismic activity for months or years, essential for capturing rare events and establishing long-term patterns. These advanced systems might finally confirm whether the moon experiences slow quakes tied to core readjustment, similar to Earth's slow earthquakes that gradually release energy over extended periods. Such phenomena could explain the mysterious seismic pulses that have captured scientific attention and prompted warnings from researchers like Michio Kaku about the moon's changing internal dynamics. Advanced monitoring technology. Michio Kaku often highlights that humanity exists in a rare cosmic window, a fleeting moment in astronomical time when we can witness and study the moon's internal dynamics before they cease forever. In another billion years, the moon's core may freeze completely solid, making current observations irreplaceable scientific data about planetary death. This perspective transforms lunar exploration from mere curiosity to urgent scientific priority. We're not just studying a neighboring world. We're capturing data during a unique period that will never repeat itself. The moon provides a live demonstration of how small planetary bodies evolve and eventually become geologically inactive. The seismic signals detected from the moon's core might represent one of the final chapters in a 4.5 billion-year story. As the lunar interior continues cooling, these tremors will become increasingly rare until they stop completely. Once the core solidifies entirely, the moon will truly become the dead world scientists incorrectly assumed it already was. Scientists often discuss the importance of being in the right place at the right time. In astronomical terms, humanity exists in an incredibly narrow window. After the moon has cooled enough for us to study its interior, but before it freezes completely and goes silent forever. This unique moment gives us opportunities not just to understand our nearest celestial neighbor, but to develop models applicable to countless worlds throughout the galaxy. The lessons learned from the moon's core could help identify potentially habitable exoplanets and understand how geological evolution affects their ability to support life. The mysterious seismic signals from the moon's core represent far more than geological curiosity. They're windows into planetary evolution happening in real time. Michio Kaku's warnings remind us that we're witnessing the final chapters of the moon's geological story, a rare cosmic opportunity that won't last forever. As humanity prepares to return to the lunar surface, understanding these internal dynamics becomes crucial for mission safety and scientific advancement. The moon continues teaching us about planetary evolution, magnetic field generation, and the delicate relationships that make life possible throughout the universe.